The last two mini movies have of course focused on the idea that delta H is a molar quantity. You have to have an equation associated with a value of delta H because delta H refers to the coefficients of that equation in terms of moles. However, there are some special types of delta H in which the type of delta H defines the equation. So you don't have to write an equation for one of these special delta H's, you just have to say, hey, the delta H is one of these special ones. Okay? But before we really get into these special delta H's, we do need to define the so-called standard state. Now, the standard state is just what we use to tabulate various values of delta H's and also, as you'll see, other thermodynamic quantities later on. Okay, the standard state is depicted by this little circle here. Now, this is terribly naughty of me to just use a circle for it. The real symbol that's used is a circle with a horizontal line through it, and I could put that in, but it's very difficult to get it at the right size, in the right relationship. It just generally looks really ugly and aesthetically unsatisfying. So I'm going to be naughty. When you start having a real physical chemist teaching you, they can teach you it with the real symbol. For me, anytime you got delta H with a little circle after it, it means that this is a delta H referring to the substances in their standard state. Now, the standard state is as follows. If your substance is a solid or a liquid, the definition is it has to be a pure solid or pure liquid. So if you have 100 grams of this solid, the assumption for it to be standard state, or the demand for it to be standard state, is that 100 grams is all that particular solid. If you have a solution, it is 1 mole per liter, 1 mole per decimeter cubed, or 1 molar. For gases, most of the time the standard state is 1 bar. You will see in the States occasionally where they use 1 atmosphere, which is of course a teensy little bit bigger than a bar, but to be truly properly 1 bar pressure for a gas in its standard state. Now, temperature is the one that's really sort of wishy-washy. You can have whatever temperature you want to use for a standard state as long as you specify it. However, if it's not given, assume that the temperature is 25 degrees Celsius, 298.15 Kelvin. You will see some tables, weird tables, in which it talks about the temperature being 0 Celsius or 273.15 Kelvin. Very important to note that the thermodynamic standard state is actually not STP for gases or SATP for gases. The thermodynamic standard state, while it might look like it's the same, it's not. It's not just for gases, it's for everything. Now, the first and the most important special delta H is the standard heat of formation of a substance X. It is referred to by this symbolism here. So delta H with little f between the delta and the H, and then there's the degree sign showing you the standard state, and then it is of this particular substance X. Now, the standard heat of formation is defined as being the heat change when making 1 mole of X. In other words, that's what I was talking about with it. It defines its equation. By definition, it makes 1 mole of X. So that means you'll always see the standard heats of formation given as kilojoules per mole. Okay? And it's the heat change when making 1 mole of X from its elements in their standard state. Now, the elements in their standard state is something that you need to know. Hydrogen, nitrogen, oxygen, standard state is diatomic gases. Fluorine, chlorine, diatomic gases. Bromine, diatomic liquid. Iodine, diatomic solid. Noble gases, of course, are monoatomic gases. There are some main group solids you need to know. Phosphorus, P4, arsenic, As4, sulfur, S8, and carbon, which of course could be graphite, could be diamond, could be buckyballs, and so on. We say that carbon's standard state is graphite. All metals are solids, except of course for mercury, which is a liquid in its standard state. And if you define your standard state a smidge higher than 25 degrees Celsius, cesium and gallium, which have very low melting points, might also be liquid at that point. Really important that you know what those standard states of the elements are. Some other special delta H's that you will encounter from time to time. You have the heat of combustion of a substance X, which is where you combust 1 mole of X. So in other words, 1 mole of X reacting with oxygen to make the oxides of its elements. It is always exothermic. Heat of combustion, always exothermic. Now you will see some tables that list heats of combustion as positive numbers, knowing that they are always exothermic. That's stupid. A heat of combustion should be a negative number to emphasize that it is exothermic. Now a little teeny twist here. If we look at this reaction associated with the combustion of propane, I'll tell you that delta H is minus 2200 kilojoules because the equation as written is 1 mole of propane. That means that the heat of combustion of propane is minus 2200 kilojoules per mole. But let's go back to the heat of combustion of butane that we talked about earlier, where the delta H was minus 5600 kilojoules. Okay, now that delta H is associated with 2 moles of butane combusting. Thus, the actual heat of combustion of butane is minus 5600 over 2, or 2800 kilojoules, because that's kilojoules per mole, 1 mole of butane. This equation tells you there's 2 moles of butane. Now, as a result of that, you will sometimes see thermochemical equations in which, because the important thing is getting 1 mole of the stuff that you're reacting, will sometimes have fractional coefficients. Thus, there's nothing wrong with writing this as such, dividing the butane all the way through by 2. So now it's 1 mole of butane, 13 halves O2, 4 CO2, 5 H2Os, because now you can say that delta H for that is minus 2200 kilojoules. That is the heat of combustion of butane. Incorrect to use fractions most of the time, except when you're talking about delta H and thermochemical equations. 3 other ones that you'll see periodically and we'll use importantly: the heat of fusion of X. Fusion is when a solid goes to a liquid, always of course endothermic. You have to heat up a solid to turn it into a liquid. Similar fashion, heat of vaporization is where you go from the liquid to the gas, again always endothermic. You've always got to heat up a liquid to turn it to the gas. And you might remember from last term, or just general knowledge, that there's such a thing as sublimation. The heat of sublimation of X going from the solid to the gas, and again that will always be endothermic. So some special delta H's, the heat of formation, by far the most important one. You should be aware of those. Those are always described as per mole. So heat of formation, making 1 mole from its elements in a natural state. Heat of combustion, combusting 1 mole. Heat of fusion, turning 1 mole from the solid to the liquid. Heat of vaporization, 1 mole of the liquid to the gas. Heat of sublimation, 1 mole of the solid to the gas.